Alright guys, so in this video we'll discuss something called the Squeeze Theorem. So here's basically what the Squeeze Theorem says. So the Squeeze Theorem says if you have a function h of x which is less than or equal to f of x which is less than or equal to g of x for all x in an open interval containing c except possibly c itself, and if the limit as x approaches c of h of x is equal to the limit as x approaches c of g of x which is equal to L, then by default the limit as x approaches c of f of x which should equal to L. So it's a lot of math language there to really just kind of say the following. Okay, this is very important. Notice the order of this. Okay, less than or equal to, less than or equal to, right? So you got h, f, and g, right? So if the limits of both of these, as you can see, h and g, happen to be the same, then by default, the one in the middle should be the same, should also be L. That's why it's called the Squeeze Theorem, because they're squeezing this one into just being one. It's also known as the Sandwich Theorem. The sandwich is in between the two functions. So for those of you that are more of a visual learner, here's like a visual example, right? So you've got these two functions right here. And then you got this f sandwich in between, or squeeze in between. So notice how at the value of c that where we would be interested, the limit as x approaches c for all three functions would be equal to each other. Now, how can this theorem, or why is this theorem really useful? Well, we can use this theorem to find limits. So in this example, like the function f could be something that we don't really know how to find the limit of, or algebraically it's just turning out to be very difficult. So if you can find yourself two functions so that you can sandwich the function of f in between, then if you can solve this two algebraically and prove that the limit is equal to L, then by default L should also be equal to L by the Squeeze Theorem. So we're going to do a couple of examples so you can kind of see it at practice. Okay, so here's our first example. So first of all, it's very important this information is given to us. Sorry, I kind of messed up there, but it says suppose that f of x is less than or equal to g of x, which is less than or equal to h of x, and you're given that f of x is equal to negative 1/3 x cubed plus x squared minus 7/3, and that h of x is equal to cosine pi over 2x. They're asking you to determine the limit as x approaches 2 of g of x. Well, first of all, we don't really know what g of x is, but what we do know, given on the information, is that g of x is in between these two. So that should be a hint to maybe we should be able to use the Squeeze Theorem. In order for this to work is we have to prove that both this and this at x equals 2, if we take the limit as x equals 2, would be the same value. And if it is, then by the Squeeze Theorem, the limit of x approaches 2 of g of x should also be the same. So let's go ahead and try that. So first, we're going to find the limit as x approaches 2 of negative 1/3 x cubed plus x squared minus 7/3. Okay, so think this through. First, we're just going to try substitution. This looks easy enough. So we're going to have negative 1/3, and then we have 2 to the third power, which should be equal to 8, plus 2 squared, which is 4, minus 7/3. So in this case, we got negative 8 over 3. I'm going to go ahead and use this, minus 7 over 3 plus 4. So in this case, we got negative 8 minus 7 should be negative 15. So you got negative 15 over 3 plus, we're going to make this into thirds. So 4 times 3 is 12. So 12 over 3. And if we add those together, that will give us a negative 3 over 3, which ultimately gives us a negative 1. So that means that the limit as x approaches 2 of the function of f of x is negative 1. Now we're going to try the same value for c, so the limit as x approaches 2, but now with the h of x function, which in this case is cosine, I'm sorry, not an equal sign, the limit of cosine pi over 2x. So if we plug in the 2, so that would be equal to 2 times pi over 2 would be pi. The cosine of pi is negative 1. So hopefully you haven't forgotten your unit circle from pre-calculus. So here's what we found out. We found out that the limit as x approaches 2 of f of x is negative 1, and the limit as x approaches 2 of h of x is negative 1. Therefore, since g of x is less than or equal to h of x, but is greater than or equal to f of x, by the Squeeze theorem, the limit as x approaches 2 of g of x should also be negative 1. All right, here's our next example. So example number 2, notice how there is absolutely no mention of the Squeeze theorem at all. So you are just given a limit to evaluate. So it says evaluate the limit as x approaches 0 of x squared times cosine of 1 over x. Okay, so we have a problem here. So if we plug in 0, 1 over 0 is not possible. That's undefined. Therefore, we're not going to be able to take the cosine of that. So direct substitution is not going to work, right? This isn't any factorable, or this isn't something that I can rationalize. So we have really a couple of options left, okay? Don't forget, last time I spoke to you guys, is if you get stuck with the algebra, you could always try to grab this and see where it takes you, right? So that is an option. We can try to grab this and see what the limit is, okay? Now, obviously, I'm making a video over the Squeeze theorem, so I'm going to try to see if I can use that, okay? So here's my thought process. The fact that this function has cosine in it, I have to remember, hopefully you remember this from pre-cal, that the function of cosine, so you know that the cosine of x fluctuates between -1 and 1, which means that it's greater than or equal to -1, but less than or equal to 1. Okay, so hopefully you remember that from the graph. Now, we're not analyzing cosine of x. However, even though we have 1 over x, no matter what we plug in here other than 0, we're still going to be able to compare it to -1 to 1. Think about that. Okay? You can take the cosine of pretty much any angle, right, except something that's undefined. So no matter what you put in here, right, whatever the cosine value of that is, it's going to fluctuate between -1 and 1. So it's going to be perfectly okay for me to say this expression. Okay, now let's talk about that. So you might be like, okay, but hold on, 0 is a problem, right? We can't plug in 0. Yes, but however, remember, we are talking about limits, and one of the things we talked about limits is that we don't necessarily care about what is happening at 0, but we care about what is happening as we approach to 0, which is what's going on here. So even though 0 gives us a problem here, we can kind of ignore that for the moment. Okay, so however, this isn't the statement that we care about analyzing. We care about this statement, okay? So what I'm going to do is, because I need an x squared, I am going to multiply this entire thing out by x squared. So that's going to give us -x squared is less than or equal to x squared times the cosine of 1 over x, which is less than or equal to x squared. And bingo, look at this. I mean, literally this statement right here should immediately make you think of the Squeeze theorem. Why? You have 3 functions, and the function that you're interested on, the function that you do not know how to find the limit of, is squeezed in between 2 functions. So remember, the Squeeze theorem says that if the limit of these 2 functions is equal to each other, then by default, the function that's squeezed in between the 2 should also be the same. So I'm going to take the limit as x approaches 0 of -x squared, and the limit as x approaches 0 of x squared. If they're the same, then we're going to be able to use the Squeeze theorem. So by simple substitution, this gives me a 0. By simple substitution, that gives me 0. Therefore, since -x squared is less than or equal to x squared cosine 1 over x, which is less than or equal to x squared, by the Squeeze theorem, the limit as x approaches 0 of x squared times cosine 1 over x should also be equal to 0. Notice the way I'm responding to questions. Now, if this was a multiple choice question on the AP exam, I mean, you don't need to back yourself up. But if it happened to be a free response, it's always good to mention the theorem that you're using to back yourself up as to why you're choosing the answer that you're choosing. Okay, well, there you have it. That is a couple of examples for the Squeeze theorem. Hopefully this has cleared up for you any questions or any misconceptions. It's a relatively easy theorem to use in my opinion, but sometimes it gets overlooked. Okay, and actually, I'm sorry, I almost forgot to mention this. So as of right now, based on where you are located in your calculus course, thanks to the Squeeze theorem, there are 3 limits that you need to memorize. Okay, or you can memorize. Honestly, you don't have to necessarily for the AP exam, because by then you're gonna have more skills. But for the moment, it would be a good idea to memorize them. And the reason why they work is, again, because of the Squeeze theorem. Okay, if you like to, you can always do a quick search as to why this work. But for the moment, I'm just gonna go ahead and provide those limits for you. So the limit as x approaches 0 of sine x over x is equal to 1. The limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. And lastly, the limit as x approaches 0 of 1 plus x to the 1 over x power is equal to e. Okay, there's some proofs of this out there on the textbook if you want to look at them, or you can find them online. But all 3 of this you can memorize and they can be useful. Again, the Squeeze theorem was used in order to determine this, but later on I'm going to show you something called L'Hopital's rule that would make this a lot simpler. Okay, other than that, thank you for watching. Go do your homework.